Okay, well, in this talk, I'm going to talk about the Crashbank. It's a benchmark about the LLMs that is about filling the capacity of finding bugs using different conditions, because it's unclear if this technology actually works, in which capacity works, and which one of the thousands of models actually work better. So actually, we are survey are using Crashbank benchmarking and best. And also, we're going to present Ortega, that is basically a tool for finding these vulnerabilities and reporting. Not a squad, just finding. Okay, so I'll do the presentation. I am Alfredo from Argentina. I started working in nested development almost 20 years ago. I used it to crack Commodore 64 game before that. So I never worked in vulnerability research, because half of the paycheck is you don't have to say that you work in vulnerability research. My hobby is because I have a PhD. I like to torment OpenBSD developers. Now, OpenBSD is our private system that is focused on security. So the guys that actually made OpenBSD are very capable developers. They focus on security. So when you do a tool that actually works finding bugs, it's better than you test in the best code that there is. So that's why I always torment this guy. Not because I hate him, because actually I think they are very good at work. So the money demonstration will be using OpenBSD. Okay, so let's talk about the previous work. This is very recent, because when LLM technology is very recent. In fact, you can see there is a blog post about Google Big Theories just last week. And the very first job about this is from Meta. This was presented in Black, and it's already version 2, because I think they did a presentation in 2023, and now this year again. It's basically more generic, this one. Serious about 2. It's a more generic view about tasks, cybersecurity tasks, not only vulnerability find, but also protection. They try to solve CTF problems. It's more comprehensive. Now, the Google Project Zero actually focused with the project, this one. He actually focused in trying to exploit vulnerabilities, found vulnerabilities, and then exploit them. And basically, they conclude that LLMs, this is the conclusion, are linked to disruptive exploitation. Basically, it's not that they fail, but the results are very basic exploitation. There's a stack overflow without any protections. So they conclude that they basically don't work. I don't say that they are lying, but I say that this is results from last week, and a week is a lot of time in artificial intelligence. So let's see what happens. Okay. So the Crashbank is an InfoSec benchmark. Basically, what I do is to assemble a lot of examples from exploitation. I took the complete Jira ABOS, or Advanced Buffer Overflow exercise. We always start working on extra writing, be completing each one of these exercises, portfolio, 30. Basically, I gave them to the artificial intelligence, as you can solve this. If the IE got it right, it got a point. If it's got it completely wrong, it doesn't have any points. So I have real vulnerabilities. I have one from Chromium. It should be about much more real vulnerability, about 100. But I didn't have any time, so I only put 3. That is enough. Also, I did this check only in C. But surprisingly, the artificial intelligence also works in Rust and other languages, depends on the complexity, of course. But this one is only in C. You configure, you are very easy to configure. You put the prompt here. The prompt is basically the instruction that you give to the intelligence of the LLM or artificial intelligence. And then you show every example with exactly the line where the bug exists. I mean, it's very simple. You show a C source code. I say, okay, the bug is in line 6. This is another example, the bug is in line 30. So it's not only check the bug finding capabilities, but also the reporting, because even if the artificial intelligence found the bug, sometimes it finds the report correctly, sometimes it says that it's in a wrong line, and basically what you have to do is to read a lot of reports, so you have to report correctly, you have to follow the instructions. Sometimes it starts rambling, it starts talking about a lot of stuff. It's like a junior research basically. So here's the results. So let's see, it's a very small font, sorry about that, but there is a lot of models here. So what are models here? Model is basically every company, many companies that create artificial intelligence, release them, some companies release them open, and some companies that keep it closed. For example, ChatGPT is closed. Many meta releases an open that you can download around your computer. And this venture is focused in the local, the open artificial intelligence. Why? Because if you are doing finding bugs, you don't want to use ChatGPT because you are basically giving you bugs to OpenAI or to Gemini or to whatever close artificial intelligence. If you are runs in the cloud, basically you have to give your code to a third party. You maybe don't want to do that. You want to keep your results for yourself, or maybe you just don't want your code is private. You don't want to give it to OpenAI. So many of these results are from local open source AIs that you can run in your computer. You have to have a very good computer as well. And we can see one of the few results here is that it's very obvious that the better results are from the biggest and more artificial intelligence. This is Llama 3. Llama 3 was released a couple of months ago, so it's all very recent. The thing is, we can see how the artificial intelligence was increasing very rapidly the capability. This was Llama, this one over here is Llama 2. So this was the state of the art just 3 months ago. And look at the result. It doesn't understand anything about the code. The first one is Llama 3, but it's a very small result. It's a very small model that is basically good for conversation, but really can show that it doesn't understand, doesn't have any idea of the code. But and here in the middle, we have GPT-4. It's not the best result. This is very curious. Why is not the best result if it's the most powerful AI? Well, this is very strange. So actually, I looked into it. I looked at the results, and I found that I think it's very likely that it's the one thing called alignment. Basically, the artificial intelligence got instruction that not to speak about certain things. You can give instruction to make a bomb. You can make instruction to make an exploit. For example, you will deny about that. It's called alignment because it's supposed to be a good artificial intelligence. So the problem with Llama 2 and OpenAI is that it's very strongly aligned. I mean, if it won't give you the answer of where the bug is because the artificial intelligence thinks that you will use to do malicious stuff. That is maybe true. But the AI will deny. I will say, I didn't find any bug here, when it's obvious there is a bug. So, at the end, the best results are for Llama 3. Mistral also have a very good score in this benchmark. Of course, the benchmark has improved a lot, but the first benchmark will give you a very quick view of the capabilities of the systems. Basically, the benchmark is already outdated because the artificial intelligence found all the bugs. That's basically this. I had to make it harder because it's already too simple for the best artificial intelligence. They found everything. I had to make more difficult tests. Now the quantization effects, basically how you run an artificial intelligence and you can compress it. Because artificial intelligence, it takes a lot of memory to run and a lot of hardware to run. thousands of dollars, and actually it's very slow. So you can compress using a technique called quantization. That allows you to run a much faster and a much cheaper computer. But of course, it decreases the quality. It's like a JPEG picture. You get it smaller, but it has less quality. So I tried to measure how much you can compress it. And it started working. And you can see here that actually it didn't affect a lot. This is like only 5 bits, compression of 5 bits. The original LLM has about 16 bits. So here you can compress about 3 times with 5 bits. And on this side, we have 2 bits. I mean, it's a very, very strong compression. And we can see that actually the results, the score doesn't decrease a lot. It goes from 45, the least compressed here, to about 40, the more compressed. So you can use this to basically, you can compress this model a lot. They will find bugs anyway. They have to be very good. It doesn't care, the model doesn't care that much about if you compress it or not. This is llama 3 based. I mean, other models might have worse results or better results, but this is llama 3, the used model. And we can see that actually it's not very affected by compression. There's some good. Okay, this is another plot. Sorry, there's another plot in the presentation. But we can see this plot in the green is basically the score that they have in generic score. I mean, for example, you can see that the biggest in generic score, you have GPT-4 here. Of course, it's one of the best and the biggest. Here. It has the biggest score on general intelligence, but not very good at finding bugs. Here, and GPT-4 and GPT-4o have the same things. Except on the other LLMs, you can see that it's an inverse. For example, this one has not a very good score in generic answering, but very good at finding bugs. Why is this? I don't know. But that is the best one. We can see that the models that are very strong aligned, I mean, with very strong limiter in the answer they can give, they are very good at answering generic questions, but very bad at finding bugs. Basically, they deny it's a bug. They have like very the limitation really affects the way they think. So it's very good to have a model that doesn't have any limitation. Okay, so you can't find real bugs. Whether they're going to see. This is a real bug. This is a real from Chrome. This is one last year. This is an integral overflow. Basically, it's a very simple bug. If you can, sorry. The problem with this bug is in 2 variables. Basically, it's an allocation size. It's a byte array size. It's the end result of the calculation. Sorry, it's byte array size. We do the calculation. It ends up in allocation size. And this calculation is wrong. Allocates the wrong typical integral overflow. This is the human report. Interview platform, allocation size, my overflow after computation 1 to 2. So what happens? What say the artificial intelligence if I give you this code? We just see it. Okay. This is the report from the artificial intelligence. I give you the code and say, okay, find bugs in this code. And just tell them that, find integrals in this code. Okay, we can see here that basically the artificial intelligence is called perfectly exactly the same as the human. The length size and the location size has a problem. We actually got it. And also start rambling about where it is and how to fix it, blah, 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 blah. But the important thing is that the artificial intelligence works exactly the same as the human. And this is a real case. It's Chrome, one of the most common code there. So we can see, okay, well, if they actually work with maybe a line, so maybe we can run the actual demo here. Let's see if this works. This is a demonstration. it's needed, and I hope internet is working here. So I have this code here, the issues, and basically I have the code. It's very complex, the code, but you can see that the problem is in arena size and allocation. It's the same code as before, right? So we run this auto-hacker, hacker means hacker in Spanish. Basically, but it's a very simple code. We can choose between model here, GPT. We have this is basically Llama 3. It's a free service. You detected how only one function body picks a test, or you just do a launch. It will take a while because it's actually running. It's not running locally, it's running in a server. Actually, it's running a server in Argentina. Okay, so it basically, well, the first time we can repeat the guide. It found out that the ellipse is very large. We didn't found the vulnerability. So what we do now, we can run it a lot of time. This is run. So we can run it again. Yes, it will. Every time you will find different things. So let's launch it again. This is, by the way, is not a very good model. Not a very good model. We can try to do before see what happens. Well, this model doesn't work very well. Let's try it before. Again, we have a lot of models to choose from. GPT-4. Let's see what happens. I think this is a little faster. GPT-4 try to speak a lot. It's around it a lot. Here. Auto modularity. Allocation size is the problem, arena size is exactly the same report that you can do. And this was GPT-4. This is actually not the best model on there. In fact, right now, we have models that are way better than GPT-4 in code. We have, for example, Cloud 2 is much better than GPT-4, and we have open models that are actually much better than GPT-4. So the model actually starts rambling about a lot of problems, fixed the integral overflow. It describes perfectly the vulnerability in the problem. So let's continue. For another example. Well, this is another example, OpenBSD. So this is a this is interesting because OpenBSD has a lot of fuzzy inside. It has one of the most fuzzy projects. But if we show this code to the deficient intelligence, you will still find bugs because some bugs are very hard to trigger in the fuzzy. Particularly this one is a syscal, has a heap overflow and calculation of this variable here. It will cause this allocation to fail and cause and keep overflowing the kernel. So let's see what's happening. We're going to try Cloud. Cloud is one of the best models out there. Cloud, I think it's 3.05. And just this is basically the problem. Look for bugs in the code. And what says Cloud? Cloud says, well, there's a problem here in this structure here because this value is a controller and we can cause a heap overflow in the kernel, right? So I gave it to this result to the OpenBSD developers, and they actually, it was a vulnerability, they fixed it. You can see here that it says that I reported this line, it was our job in the artificial intelligence. I did nothing. I didn't even know how this vulnerability works. We basically just show it the code, this is kernel code. Even if they have, I think they have a version of syscaller for OpenBSD, but this is a very old bug. It was like 7 years ago. It didn't, the fuzzer can't find it because basically the only way you can find it is to understand the code because it's very hard to trigger. The artificial intelligence found it in, I don't know, 5 seconds. This was a very old artificial intelligence. It was basically extra. It was like 3 or 4 months ago. You say, oh, well, so you reported this. How many bugs I'm sitting on? How many bugs I have? Because I run the artificial intelligence and all the kernel. But I don't know. There's a lot. The problem with this system is that you need to do triage. I mean, the artificial intelligence will report thousands and thousands and thousands of bugs. But not everyone is a security guard. Let's see. You have to, it's like a puzzle, you have to go through each one of them and see what is working, what doesn't work. But it's much easier to go to the reports than to go to gigabyte of code. So it's actually, it makes you work much easier. The system that I showed you is very simple. It just basically clean the source code, assemble at the prompt. If you want to find a raw flow, into the raw flow, whatever you want to find, you just assemble the prompt like a text file and send to the model. And just write the answer in the model on top. So you instead of see the code, you will see the report. Now, what are the problems of this approach? Well, the problem of artificial intelligence is sometimes it lies. They are called as hallucinations. Sometimes artificial intelligence will say things that are not true. What I find is the hallucinations are very few. Almost never get it wrong. The artificial intelligence, if it reports some bug, it's very likely that the bug actually exists, but maybe it's not reachable for some reason. That's the main problem. It's false positive. I mean, it's the same for fusel. With a fusel, you have a lot of results that are really not exploitable. So you have to basically throw them away or maybe you can fix them. The same with the artificial intelligence. It will report thousands and thousands of vulnerabilities that are actually not exploitable. But it almost never has isolation, specifically the neural models. It's almost not a problem anymore. Well, false positive. Oh, I'm very bad at putting something well. False positives. This is the main problem because the artificial intelligence doesn't know if some code is exploitable or not, because this doesn't do verification. They just do report. So this is basically a job that you have to do by yourself. But it's much easier to look at the code. And the other problem is our requirements that if you don't want to use a cloud service like OpenAI, like ChatGPT, you need a very big computer. You need at least 50 gigabytes of RAM. This is a GPU to run a model that actually understands the code. I mean, you can use a MacBook, you can use a CPU, but it's too slow. I mean, you can see this is one function. It takes about 10 seconds. Imagine if you want to give a complete kernel, it will take about a month. A month using the GPU. If you use a MacBook, it will take 6 months, 1 year. It's actually quite slow. So you want the faster AI possible, and that means that you need a big server with a lot of GPUs. So this is about auto-taker. I mean, we already know that it actually works. Not every vulnerability, of course, will be discovered, but this business logic will not be discovered by this system, mainly because the LLM doesn't know about business logic. Probably if you can teach them, you can find it. But at this stage, it doesn't know about business logic, it doesn't know about logic bugs, but it will find integral flow, buffer overflows. It basically will find automatically over gigabytes and gigabytes of code. So what is exactly what we did? We did this part with vulnerability discovery. This works right now. But exploit writing is not only that. We can see that it's actually the easier part of exploit writing. This is sorry. Skills required. You don't require a lot of skills to do vulnerability discovery. I mean, current models can do it perfectly, but then you have to do a trial development, or what also is called a proof of concept. It's not an exploit, but it's like a confirmation that the vulnerability actually exists and is a security. This is very much harder to do. You need to explode the code, you need to create a lot of code to trigger. And even harder still is actually do the exploit, because you have to fight against protection, against the operating system, reliability, etc., etc. We care a lot about this. So basically, this part in top is what basically Google Project Zero and Meta are trying to do. This one, they fail, of course, because models are not smart enough. I just try to do this one, and this one works perfectly. So basically, the idea is that you leave this part to the AI, and this part in humans. Okay, so eventually the artificial intelligence will be able to do this part here too. But there is a problem here, and it's marked here. That is patch. I mean, the artificial intelligence, it can find bugs, but that's not patch them. Because patching a bug is much easier to exploit. I mean, we can see when you find a vulnerability, you give to a developer. The developer doesn't need to be an expert writer, doesn't need to even know about security. You can patch the bugs very easily. It's actually requires less skills to find them, the vulnerability. So if we make this observation, can we make a similar software that do automatic patching? Well, we should be able to do it because it's much easier. Yeah, so this is a presentation about an additional software called AutoPatcher. Basically, what this does is very similar to the auto-hacking, except that this not only discovers the vulnerability but also patches them automatically. And the problem is that sometimes the code generation doesn't work. So this has additional step here that do a closed loop confirmation of the patch. I mean, you generate the patch, everybody knows ChatGPT is very good at writing code, and Cloud is even better. So you find the vulnerability, write the patch, the correction, and just test it. And if they pass the test, they accept the patch. And we can do this massively in every function of the kernel. So, but actually, what happened, we run this for a month, for example. Okay, what I did actually with the OpenBSD kernel, I generated not the complete OpenBSD kernel, but just the IPv4, IPv6 stack. It generated 2,000 security checks. The kernel works perfectly. This is a rundown of what it cost me to do it. It were about 1,000 API requests. The cost you can see is very cheap. Oh, sorry. This is the total cost of fixing about 2,000. They're not security vulnerabilities, because most of them are not reachable. But we can add, it's called using a technique called defensive programming. I mean, you check every variable, every calculation, even if it's not reachable, even if it's impossible to exploit, you check it anyway, because you don't know if the future the code will become exploitable. So basically, we add a lot of checks to the kernel, and we compile it, and it actually works. You can see here, sorry. This is the version of OpenBSD with all the checks. As you go to the hard core, and this is a kernel with a refactor with all the checks added. It works perfectly like the regular OpenBSD, except that it has additional checks. I mean, this is a lot of vulnerabilities fixed. It works perfectly. It works the graphics. It has no problem. So, well, what else we can do with this? Let's see the process how we did. We have another library here called CLib. CLib is a very known library about compression. There's a lot of utilities that use this library, for example, GC. So what we can do is launch the automatic patch of CLib. What we do, sorry, we're going to close here. We're going to launch the utility and you say just patch, so find vulnerabilities and patch, whatever you can, patch, and then run the test. Because we want to know that the test works. So what is it? We're going to give you the model here, we're going to use ChatGPT because it's much better to generate code. And this is the instruction. You see that the instruction is very simple. Add code check for this function to avoid any other types. I mean, we want to feed every function and add checks, every function and add checks for every single function of the project. You detect you have 41 files, it will launch it. So it will take a while. It is the current function that is actually processing, is compressed. This means that actually it can generate a patch and the patch works because ChatGPT is very good at creating patch. So it's almost enough, it makes no mistakes. Here it made a mistake, so if it's a mistake, no problem, it tries to generate the patch again. Until it works, And you can leave it running, but let's see what it did. We're going to put it and see. This is the function. You can see that actually this is what ChatGPT had. We have a bunch of destination rule, destination. We have a lot of several parts here. Several parts. You remove this part and replace it for one that has security checks. Actually, you did a lot in this little time. You put a lot of patch here. You can see that even the calculation here, you did a lot of error corrections. And also generate the test, and this is example 64, this is a test that passed everything. So I now have a CLib library compression with other patches. We can keep it running, and you will. The interesting thing is every time you run this, we generate a different set of patches. So we have like a randomization of code. I mean, you can do a custom version of CLib. That is impossible to exploit. I mean, the return oriented exploitation doesn't work anymore because you have a different code every time you have this system. We are at the ending, so we're gonna show you one more thing. What happens if we modify this? And we have, for example, main code. Yes, you understand. And we launch it. It will actually try to make the collocation. You understand? You know, I'm going to generate a new version of CLib with easier to follow code. You can do whatever. So we can do some examples here. Sorry. This is CLib with. This is that I show it with the other security checks, but we have several other transformations. Sorry. We made it obfuscated. We can obfuscate the code very easily. You can see it, okay, now transport the code in a version of the code that is obfuscated, that's impossible to follow. And this code passes all the tests and is 100% compatible with CLib. And for example, we can tell it to make the code cute, Google, for example. And I didn't make sense. You don't understand what it did. Of course, what it means implemented. It is very cool. So I don't know what this compiles, but actually compiles. I don't know. So let's create the necessitate library. Oh, this library is 100% compatible with CLib. Like my own version of CLib, and when I send compressed stuff to the conference, I use, of course, the Cube version of CLib. And I also have security checks. So this basically doesn't have a lot of offense, but it's mostly on defense. This is a defense part of the part. But it will affect the offensive also because this automatic patching will certainly affect a lot of this vulnerability research. So we're going to see what is the key thing. Okay, go with the talk. Okay, LLM can already help code review and this code. Help is a very, very, very smart word here because basically they can do it for you. The problem will be only you have to sift through all the thousands and thousands of reports, but it's much easier to do the code directly. Now the problem is that not only can find bugs, as you can patch them. So this will really affect vulnerability, because it will decrease a massive amount of boons or bugs will be found using this technique. And also, this is the possibility that you can very easily create your own version of your kernel, like I did, or your own version of basically the operating system that is almost impossible to exploit. Of course, not logic fouls, but the memory corruption vulnerability will be almost, not almost removed, but a very big portion of vulnerabilities will be catched by this technology. Okay, well, there's a problem is very likely this exploitation, and of course, Google is incorrect, and because I had all ones to this and work. Okay. And if you're interested, you can download these tools, you can run one yourself. If you don't have a big computer in your home, you can use ChatGPT. Of course, every bug you found because try the NCA. So, but if you use for patching, I think it doesn't matter. Okay. Thank you very much.
Thank you. Thanks again, Alfredo. So, questions? Anyone with questions? Yes.
I'll proceed from my speech. I want to ask that the test in the loop means test to see the vulnerability mitigated or just test for the code, the patch the code is can be built. Because to confirm that the vulnerability is mitigated, the AI should be able to create the kind of low-level POC to trigger the bug. So.
Yeah, I'm sorry. I think I understand the question. I mean, the AI intelligence build the test and then I don't know what. I didn't get
in the loop there's a test, right? So test means find out the bug is mitigated or the patch code can be built.
Yeah, the test is if the patch can be built. Most likely the bug can be mitigated because the artificial intelligence understands there is not a bug, but like a possible vulnerability. It doesn't verify that it actually exists a bug. It just resolve a variable and say, okay, this variable is dangerous. It can possibly, if you can reach this code, you can exploit it. So it generates a patch, and the current test that I have is basically you have two parts. One is just build, it's just compiles. And the second part run the test. Because this patch sometimes they break things. So to make sure that it doesn't break additional things, I run the test if the project has tests. If the project doesn't have any tests, like OpenBSD, basically I have to check the test by hand, one by one.
Thank you.
Thanks for the speech. Just to clarify, right, for this Chromium bug that was published, did GPT find the bug first, or was this I guess bug report published and you tested the code on GPT?
Yes, I tested it. This report is actually Llama 3. This was written by Llama 3. But the one that I showed you just now, it was ChatGPT. There's not a lot of difference between once the models reach a threshold of the intelligence, once the code understand the code, it really doesn't make a lot of difference if you ask to Llama 3 or ChatGPT. They all generate a report and they all find the bug. We can see it in the demonstration. It was very similar. I think that the road was very similar. But of course, you have to be a smart enough model.
Thanks for the presentation. Just a quick comment about the fact that right now you are not able to generate exploit. It's not possible to generate exploit because we don't have enough material, so we didn't train enough the model to be able to generate the exploit, or you think that we don't provide enough source code to the model to be sure that it understood the complete path of the Also part of the exploit, where the data comes from and where you can exploit it. So what you thought about that?
Yeah, okay, so the question is why this can't generate an exploit? Where if maybe we gave him more information, it can do it. And I believe, yes, of course, you only need more information. I mean, creating an exploit is sometimes like incredibly complex. You need heap manipulation, heap network manipulation, sometimes you need to know techniques that are not known to the LLM, you know, it's like secret mappings that will never change. So you really need a level of knowledge that is not only not public, but really need a lot of skills. So I think eventually the AI will be able to create some exploits. I mean, already is able to create very basic exploits. But I think it's not worth to work towards that problem because by the time the artificial intelligence can write an exploit, a much dumber artificial intelligence will be patched or exploited. So basically you can do it in your lab because if you find a vulnerability, it's more likely, imagine an incredibly smart ChatGPT 10, for example, it will be able to exploit. But by that time, all vulnerabilities will be patched, like ChatGPT 9. This is basically futurology. I don't know if this is what exactly will happen, but it's very likely. I mean, the patching is very easy to do in a current current model cannot even start operating exploit. It cannot really patch everything. So I think this is very likely it will be out in the future.
Thank you very much. So do we all have to find a new job now?
Well, that's very interesting because I can tell you something that I didn't write in this presentation is that my job currently, like blockchain, is mostly Rust. So I say, okay, I'm safe because this only works in C, C++, and Rust doesn't have memory corruption. So while we are working now on an audit, that of course I cannot tell which one. So okay, what happens if I use this in Rust? I mean, the only limitation is the parsing. I mean, I can't just this parser is for C and Rust is different from C. So I write a small parser from Rust and basically feed Rust code to this. What happens? Well, turn around, we found about 10 issues, and this project found 3 or 4 of them. I mean, we already found issues in Rust. It didn't find the critical issues because blockchain is more really like business logic, and finance, and of course it is funded. We did found a lot. I mean, this is basically generic. It doesn't have to be C. It can be Rust, it can be JavaScript. You can find vulnerabilities in SQL. I mean, it's like a semi-senior. It's not an expert, also not a junior. It's quite competent. So I had to get a new job, likely. That's why I started to work on artificial intelligence.
Thank you.
All right. If not, then thank you again.
Thank you very much.
Our dear speaker for his precious time as well. Thank you.